Hey, so I am making another video to review some earlier concepts that we looked at earlier in the class and have really been using throughout, but now I'm going to talk about finding and characterizing fixed points. So fixed points, as we know, are where the dx dt and dy dt are equal to 0. And I decided on this one it was probably easier if I wrote it all out and then sort of talked through it as I went. So that's what I'm going to try and do here. So for this example, I have dx dt equals y, so we're looking at where y equals 0, and also dy dt is where x squared minus x equals 0. So we're looking to solve those, and we have that here just y equals 0, that's easy. Here x times x squared minus x can be simplified to x times x minus 1. And so our fixed points are 0, 0, and at 1, 0 because of that. So now to find our stability, what we're going to want to do is make what's called a Jacobian matrix, which is right here, and that's defined as the partial of f, which we defined f as dx dt, the partial of f with respect to x, the partial of y or the partial of f with respect to y, and then the same for g, which is what we defined this as. So if you do those partials, you get that our general Jacobian is 0, 1, 2x minus 1, and 0 again. And then we're going to want to analyze this around each fixed point. So we'll start over here, fixed point 0, 0. So you're going to plug 0 in for x and y wherever they appear. So if you remember, there was a 2x here. So we plugged in a 0 for 2, and we just got minus 1. And then you're going to want to take the determinant of this. So you do, if we letter these positions a, b, c, d, you're going to do a times d minus b times c. So you end up with lambda squared equals -1, so lambda equals plus or minus I. And we know that if it's plus or minus I and there are no real parts, this is going to give us the stability of a center, which it looks like a circle. If there were real parts, it would either be a source or a sink, which looks like a spiral either outward or inward. But this is I, so it's a circle. So that's awesome. And in order to calculate the direction that the circle is going, clockwise or counterclockwise, you want to look around the point you just tested and just calculate what dx dt and dy dt are. So I did 0.1 for both, and I got that dx dt equals 0.1 because dx dt is just y, and y is 0.1. And dy dt is -0.1 plus 0.1 squared. So y ended up being 0.0099, negative 0.0099. So you see that x is increasing, y is decreasing. Because of where this is, you know that your circle is going clockwise. So that is the 0.00, and then if we come over here, we want to look at 1, or it should be 1, 0, sorry. 1, 0. So you plug those in, and you get that, you do the same thing, find the determinant, you get lambda squared minus 1 equals 0. So lambda equals plus or minus 1. And because it's just real parts, and there's a positive and a negative, we have a saddle here, which is unstable. So now that we have a saddle, that means that in one direction it's going out and in one direction it's coming in. So we're going to have to find the eigenvectors in order to figure out on which lines it's coming in and which lines it's going back out. So we're going to use some matrices again. And in order to do this, you take the Jacobian that you had and you plug in the lambda value that you're looking for. So here, we're going to need to do positive and -1. So this one we're doing +1, so we plug that in for these lambdas and find this matrix, and we want to find what this vector has to be in order to make this true. So you're going to do two equations, two unknowns, -1 times v1 plus 1 times v2, that's our first one, and then 1 times v1 plus negative 1 times v2. So we end up with negative v1 plus v2 equals 0, and also that v1 minus v2 equals 0. So our first eigenvector is just going to be 1, 1. Based on this, it could be a lot of things, but we're just going to go with the simplest case, which is 1, 1. So now we're going to move on to the second one, which is where we plug in negative 1. And we just get a matrix of 1s here. So when we go through again and do 1 times v3 plus 1 times v4, and then 1 times v3 plus 1 times v4, and you get that v3 plus v4 equals 0, and v3 plus v4 equals 0. But because of that, we know that v3 equals negative v4. So 1 is negative, 1 is positive. So I did negative 1, 1 is our second eigenvector. So we have these, we have our eigenvalues and our vectors, and we know which ones go together. So from that we can make a sort of general equation. So positive 1 is going to be, so how do I word this better? So along the line y equals x, basically, which is what this vector is going to denote, it's going to be growing, and along the line negative x, it's going to be decreasing. Because we know that our negative t is our decreasing side, and then our positive, so that negative t actually symbolizes the negative 1. Lambda equals negative 1. This really is e to the lambda t. Both of these are. So one of our lambdas is negative 1, one is positive 1. Our negative is decreasing, our positive is increasing. So if we graph, we see that this is our line 1, 1, and it's increasing. This is our line negative 1, 1, and along that it is decreasing until it gets close to here, and then it changes to increasing. So that's how you get that. And then the last thing that you need to look at are the null lines. So null lines are just where dx dt and dy dt equals 0, and are where so fixed points are where null lines intersect. So it makes sense that those are our null lines, because they're going to end up being y equals 0, and then x equals 0, and x equals 1, which are what our fixed points are. In other cases, you can also have other null lines that aren't just horizontal or vertical lines, if there's some combination of x and y that will make this true. But for our case, we just have horizontal and vertical, and they look something like this. And then in order to get these directions, you're again, like we did for this guy, where we found the dx dt and dy dt a little ways off the point. We're going to find dx dt and dy dt a little ways off of the line. And if you do that, you'll find that these are the arrows. We already know what this one is because we know which way our circle's going, so that's helpful. And then we just want to look at this one, and we find that those are the directions. And so then if you drew this all together, you would have circles here that are going clockwise, and these here are going like this. So you can sort of start to imagine what that would look like if you were to draw a faceplane for it. So this has been a little review of fixed points and null lines. I hope it was helpful, and happy studying. See you guys tomorrow.